Hello young mathematicians and welcome to number theory and cryptography. We've seen in previous lectures that congruences are a central tool in cryptography but also in number theory. Thus, in this lecture, we investigate this device in depth and explore its subtleties. Before we establish it on a firm ground, let us see together how powerful it is on concrete examples. In our first example, we would like to prove that for every integer a cubed minus a is a multiple of 3. Indeed, easy computations yield that 0 cubed minus 0 is equal to 0, and this is a multiple of 3. 1 cubed minus 1 is also equal to 0, and this is a multiple of 3. 2 cubed minus 2 is equal to 8 minus 2, which is equal to 6, and 6 is a multiple of 3 because 6 is equal to 2 times 3. 3 cubed minus 3 is equal to 27 minus 3, which is equal to 24, and 24 is also a multiple of 3. 4 cubed minus 4 is equal to 64 minus 4, and this is obviously equal to 60, which is a multiple of 3. 5 cubed minus 5 is equal to 125 minus 5. This is 120, and 120 is obviously a multiple of 3 as well, etc. In high school, we represent integers on a straight line on this fashion. Here we have 0, here we have minus 1, minus 2, 1, 2, 3, etc. But instead of doing this, one can wrap the straight line around the circle, as we shall see in the next example. In our case, we would like to show that a cubed minus a is always divisible by 3, so let us wrap the straight line around the circle of 3 hours. Indeed, we first start by representing 0 here, we represent 1 here, this is 2 hours, we get back on 0 to represent 3 hours, the number 4 is here, the number 5 is here, the number 6 gets back here, this is 7 here, this is 8, 9 corresponds to 0 hours, 10 corresponds to 1 hour, 11 corresponds to 2, and so on and so forth. So what we've done here is instead of representing numbers on a straight line, we wrap those numbers around a 3 hours clock to get the representation that you see here. But how is this going to be helpful? Indeed, we see that every multiple of 3 corresponds to 0 o'clock, every multiple of 3 augmented by 1 corresponds to 1 o'clock, and every multiple of 3 augmented by 2 corresponds to 2 o'clock. Numbers here are of the form 3 times an integer k, numbers here are of the form 3 times an integer k plus 1, and numbers here are of the form 3 times a certain integer k plus 2. And you can check this by yourself on the numbers here. From here, we deduce that numbers are either on 0, either or 1 o'clock, or on 2 o'clock. And we can actually represent every positive integer in this fashion. Let us now get back to our claim, and let me remind you that we would like to prove that a cubed minus a is a multiple of 3. Indeed, one can write this as a times a squared minus 1, which is also equal to a times a minus 1 times a plus 1. Now, on a 3 hours clock, a either points on 0, either points on 1, or on 2. If a points on 0, this means that a is a multiple of 3, in which case all this product is also a multiple of 3, and hence a cubed minus a is a multiple of 3. Now, if a points to 1 o'clock, this means that a minus 1, so this is a minus 1 points to 0 o'clock, in which case a minus 1 is a multiple of 3, and so is the whole product here, which means that a cubed minus a is a multiple of 3 too. The last case is when a points to 2 o'clock, so this is a, and we would like to know why is a cubed minus a is a multiple of 3. This is obvious because actually when a points to 2, a plus 1 is here, so a plus 1 points to 0, which means that a plus 1 is a multiple of 3, so is this whole product, and so is a cubed minus a. Bingo! I claim that we're done because in all cases here, a cubed minus a is a multiple of 3. Let us now move to a similar fact and prove it using the clock. A to the 5th minus a is, guess what, a multiple of 5 actually. Straight computations give us 0 to the 5th minus 0 is actually equal to 0, which is a multiple of 5. 1 to the 5th minus 1 is also equal to 0, and this is a multiple of 5 too. 2 to the 5th minus 2 is equal to 32 minus 2, which is equal to 30, and 30 is also a multiple of 5. 3 to the 5th minus 3 is equal to 243 minus 3, and this is equal to 240, which is also a multiple of 5. And I'll let you check this fact for more integers. To prove this claim, we will use a 5 hours clock, in which the first hour is 0, then we have 1 here, 2, 3, 4, 5 gets back on 0. This is 6 here, 7, 8, 9, and 10 gets back on 0 too. Here we get 11, here we get 12, here we get 13, 14 here, and so on and so forth. So what we see here is that on a 5 hours clock, all multiples of 5 points on 0, and the others, either they point to 1, either they point to 2, to 3, or to 4. To simplify computations, when a number points to 0, we will write that a is congruent to 0 modulo 5, and this means that a points to 0. If a points to 1 o'clock, we will write that a is congruent to 1 modulo 5. If a points to 2, we will also write that a points to 2 modulo 5, and so on and so forth. Let us now get back to our claim, and let me remind you that we would like to prove that a to the 5th minus a is a multiple of 5. In the same fashion as a cubed minus a, we write this as a product which is equal to a times a to the 4th minus 1, and this is equal to a times a squared all squared minus 1 squared, which is equal to a times a squared minus 1 all times a squared plus 1, and this is also equal to a times a minus 1 times a plus 1 all times a squared plus 1. Now, to prove that a to the 5th minus a is always a multiple of 5, we have to show that on a 5 hours clock, it always, whatever happens, points to 0. And to do this, we will prove in each case that at least one of these factors here is a multiple of 5. Indeed, if a itself points to 0, this means that this product points also to 0, which makes the result very easy because this gives that a to the 5th minus a is also a multiple of 5. Now, if a points to 1, a minus 1 points to 0, and this means that a minus 1 is a multiple of 5, which also means that this whole product is a multiple of 5, and thus a to the 5th minus a is again a multiple of 5. The third case is when a points to 2 modulo 5, in which case a minus 1 points to 1 modulo 5, and a plus 1 points to 3 modulo 5. So we see that none of the three factors here is a multiple of 5, and this is because none of them points to 0, so we must inspect a squared plus 1. Indeed, if a is congruent to 2 modulo 5, then a squared plus 1 is congruent to 2 squared plus 1 modulo 5, and 2 squared is 4, so this is 4 plus 1 modulo 5, which gives 5 modulo 5, and 5 modulo 5 means that a squared plus 1 points to 5 modulo 5, which is 0 modulo 5. Bingo! So we see that if a points to 2, then a squared plus 1 points to 0 modulo 5, which means that a to the 5th minus a is also a multiple of 5. Now, if a points to 3 modulo 5, we easily see that a minus 1 points to 2 modulo 5 and a plus 1 points to 4 modulo 5, which aren't very helpful for us, so we have to inspect again a squared plus 1. Indeed, if a is congruent to 3 modulo 5, then a squared plus 1 is congruent to 3 squared plus 1 modulo 5, and this is 10 modulo 5, and 10 modulo 5 is also 0 modulo 5. Wonderful. The last case is a trivial fact because if a points to 4 o'clock, then a plus 1 must point to 0 o'clock, in which case the number here is a multiple of 5, and this gives that a to the 5th minus a is also a multiple of 5. Great news, and what a wonderful clock. I recommend that you prove by yourself in this same fashion that a power 7 minus a is a multiple of 7, and we will see in future lectures that those are particular cases of the little but great theorem of Fermat, which asserts that if p is a prime number, then p must divide a to the p minus a. Our course will be example based, so let us check another example. We would like to show for p a prime number greater than 5 that p squared minus 1 is always a multiple of 24. Seems very weird, but let us check this with some examples. If p is equal to 5, which is the first case, p squared minus 1 is equal to 5 squared minus 1, which is 25 minus 1, and this is 24, which is a multiple trivially of 24. Now the next prime number is p equal to 7, and we have here p squared minus 1 is equal to 7 squared minus 1, and this is 48. 48 is equal to 2 times 24, and it is a multiple of 24. Now when p is equal to 11, which is the prime after 7, we have p squared minus 1 is equal to 11 squared minus 1, which is 121 minus 1. This is 120, and 120 is 5 times 24, and is also a multiple of 24. 4. The next prime number is p equals to 13, and here p squared minus 1 is equal to 13 squared minus 1. This is 169 minus 1, which is 168, and this is equal to 7 times 24. Bingo. Now to prove this, instead of showing that 24 divides p squared minus 1 for p prime number greater than 5, we will show that actually 3 divides p squared minus 1 and 8 divides p squared minus 1 too, from which we will derive that 3 times 8 divides p squared minus 1, and we know that 3 times 8 is 24, which is our result. It is actually an obvious fact that a multiple of 3 and a multiple of 8 must be a multiple of 24, but this needs a correct proof in the general case. So we would like to show that if A divides C and B divides C, and if the GCD of A and B is equal to 1, which means that A and B must share no divisors greater than 1, then AB, which means A times B, must divide C. Be careful here because the GCD of A and B must be equal to 1 in order to conclude, otherwise this is wrong. One can see this with a trivial example. If you take A equals to 3 and B equals to 6, we see here that A and B share a common divisor, which is 3. We know that 3 divides 12 and 6 divides 12 as well, but this does not mean at all that 3 times 6 divides 12, because 3 times 6 is equal to 18 and 18 cannot divide 12. Let us now move to a proof of this fact. It is actually a consequence of the Bezout identity seen in the previous lecture, from which we know that if the GCD of A and B is equal to 1, then 1 must be equal to A times a certain integer n plus B times a certain integer m, in which case if we multiply both sides by the number c, one gets here that c is equal to A times Cn plus B times Cm, but we know that A divides c, which means that c is equal to a certain integer k times A, and from B divides C, we know that C is also equal to a certain integer k prime times B. And if we plug both of these here, one gets that C is equal to AB k prime n plus BAK m, which we can factorize by AB. So we get AB times k prime n plus km, and this means that AB divides C. Actually, we can derive this differently from the Gaussian lemma seen in the previous lecture too, because if C is equal to k times A and C is equal to k prime times B, then we have that Ka is equal to k prime B, which implies that A divides k prime B, but since the GCD of A and B is equal to 1, the Gaussian lemma implies that A must divide k prime. From here we see that k prime is equal to A times a certain integer d, and if we plug this here now, one gets that this is equal to AB times D, and this means that AB divides C. Let us now get back to our claim, and let me remind you that we would like to show that 3 divides p squared minus 1, p prime number greater than 5, and that 8 divides p squared minus 1, from which we would like to derive that 24 divides p squared minus 1. So we start by proving that 3 divides p squared minus 1, which is equivalent to the fact that p squared minus 1 is congruent to 0 modulo 3, which means that p squared minus 1 points to 0 on a 3 hours clock. First, p cannot be congruent to 0 modulo 3, because otherwise p would point to 0, which means that p is a multiple of 3, which cannot be the case because p is a prime number greater than 5. The second case is when p is congruent to 1 modulo 3, in which case we get that p squared is congruent to 1 squared modulo 3, and this means that p squared is congruent to 1 modulo 3 because 1 squared is 1, which implies itself that p squared minus 1 is congruent to 0 modulo 3. Now this was the first case, this was the second case. Now the last case is when p is congruent to 2 modulo 3. We have that p squared is congruent to 2 squared modulo 3, and 2 squared is the same thing as 4 modulo 3, and 4 hours in a 3 hours clock is actually the same thing as 1 modulo 3, which means that p squared is congruent to 1 modulo 3, and this is the same thing as here, which gives us that p squared minus 1 is a multiple of 3. So in all cases, p squared minus 1 will be a multiple of 3. Let us now prove the second claim, which is that 8 divides p squared minus 1, and this is equivalent to p squared minus 1 is congruent to 0 modulo 8, which is the same thing that p squared minus 1 points to 0 on an 8 hours clock. It is obvious that p cannot be congruent to 0 modulo a, because otherwise it wouldn't be prime. Now p can be congruent to 1 modulo a, in which case p squared is also congruent to 1 squared modulo a, which is 1 modulo a too, and this implies that p squared minus 1 is congruent to 0 modulo a, which is the desired result. Now p cannot be congruent to 2 modulo 8 because this would mean that p is equal to 2 plus a certain integer k times a, and this is an even number because it's the sum of two even numbers, but we know that p is a prime number different from 2. Now if p points to 3 hours modulo an 8-hour clock, we get that p squared is congruent to 3 squared modulo 8, which is 9 modulo 8, and 9 modulo 8 is the same thing as 1 modulo a, and this means that p squared minus 1 is congruent to 0 modulo a. For the same reasons as here, p cannot be congruent to 4 modulo a, so we move on to the next case where p is congruent to 5 modulo a, which means that p squared is congruent to 25 modulo a, and 25 modulo a is actually the same thing as 24 plus 1 modulo a, and 24 is actually 0 modulo a, so this is congruent to 1 modulo a, and it gives that p squared minus 1 is congruent to 0 modulo a. Now p cannot be congruent to 6 modulo a for the same reason as here and here too, so we know that the last case is when p is congruent to 7 modulo a, and this implies that p squared is congruent to 7 squared modulo a. 7 squared is 49 modulo a. 49 is actually congruent to 48 plus 1 modulo a. We know that 48 is a multiple of 8, so it is congruent to 0, and all of this is congruent actually to 1 modulo a, and this gives the desired result. So re-bingo again. So this ends our proof, but before we move on, I would like to add some important comments. In the 3 problems we encountered, instead of checking infinitely many cases to prove that 3 divides a cubed minus a, or 5 divides a to the 5th minus a, or that 24 divides p squared minus 1, we reduced the problem to a clock in which we only checked finitely many cases. This is a very important and fruitful idea in the theory of divisibility. Moreover, to prove the assertions here, I used addition and multiplication on a clock without saying one word why these operations are well defined or even make sense. Part 1 of our lecture Congruences 1 ends here, and in part 2 we will check why addition and multiplication make sense. Thank you for listening.